In this short video, I'm going to look at example 8.2.3, fill in a couple of details, and then do another similar example that comes from the exercises. So here we're supposed to find the inverse Laplace transform of this quotient on the right-hand side, this rational function 3s plus 8 over s squared plus 2s plus 5. And the book does a fine job of going through it, but I'll just point out a couple things. So we complete the square in the denominator and get s plus 1, the quantity squared, plus 4. And that's our denominator, for both parts of the numerator. But if we look ahead at the different forms that appear in the appendix, that s plus 1, the quantity squared, is going to, it's basically a shift. Let me get my pen fixed here. Using alpha equals 1 in the shifting theorem. And so because of that, we would actually like a s plus 1 in the numerator as well. So that 3s plus 8 I broke up as 3 times s plus 1, which is 3s plus 3 plus 5. Then using our linearity property for taking the inverse Laplace transform of this entire piece, I can break it up into two parts by separating the numerator. And on the left, we have the 3 times s plus 1, and on the right, we just have a 5. And now we would need to look up each of these two here in the table. Okay, I wrote out a little more here. Here's the alpha equals 1 shift that I mentioned, and this will use number 8 in the table. And over here, it's almost ready to use number 7 in the table. So here, this 3 we can pull out the 3. And because of the shifting by negative 1, this will be e to the negative t, because alpha is 1. And then it'll be cosine of 2t. Again, that's using number 8 in the table. And the a equals 2 gives us that 2 here. Over here, think for a little bit. We don't quite have the 2 that we need. Think how we're going to fix that up, because if we want to use the table number 7, we need to have an omega over omega squared here. And there we just have 2. So think about that a second. Okay, I hope you noticed that if we need a 2 in the numerator, we can just stick it there. And let me go back and show you what we had here again. Yeah, I can just insert the 2 there, so I have a 2 in my numerator to fit the form of what we have in number 7, table number 7 with a equals 2. So I have a over s plus 1 squared plus a squared. And I pulled out the 5, and this 1/2 I can pull out, so this just becomes 5/2. Because of the shift, I again have e to the negative alpha t, which alpha is 1. And then this becomes the sine of at. And over here we had 3 e to the negative alpha t cosine 2t. Of course, we can pull out the e to the negative alpha is 1. And then we're left with 3 cosine of 2t plus 5/2 sine of 2t. All right, so that finishes that example. Next we'll do another example that's like it from the exercises. We will do exercise 1b in section 8.2, where we find the inverse Laplace transform of 2s minus 4 over s squared minus 4s plus 13. I'll pause here for a second and let you complete the square in the denominator and set this up to use our table. Okay, so if you didn't pause it yet, make them to pause it and then come back and look at my answer here. I have completed the square to get s minus 2 squared plus 3 squared in the denominator, and that s minus 2, which is just a shift of 2, conveniently can be used in the numerator, and the numerator then is 2 times s minus 2. So this problem boils down to finding the inverse Laplace transform of 2 times s minus 2 over s minus 2, the quantity squared, plus 3 squared. I'll pause for a moment and let you find this one in the table. hopefully you found it as number 8, the cosine of AT, where s has just been replaced by s minus 2 in our example. So alpha equals 2. I've been using alpha for our shift to distinguish it between the a, which appears as coefficients in this table. Unfortunately, our book uses a for both of them. All right, so when we come back here, this is alpha equals 2 in the shifting theorem. So that means we know we need to start off with an e to the alpha t, and then that fit into the cosine, and a equals 3 came from 3 squared here. So we get e to the 2t times the cosine of 3t as our final inverse function for this example.